We talked about computer vision, and this week we are going to switch to natural language processing. So computer vision is basically about how to process data as they are images. So they are kind of spatially related. And here we are going to process sentences, and they are sequentially related. So that's one difference. And the other difference is we're going to switch from something called discriminative model to generative model. And actually, in lecture one, we talked about generative adversarial networks. Remember, we talked about how to generate fake faces. And I said there are two parts. One is separating the real face from the fake face, and the other one is just generating the fake faces. And here, we're going to talk about the generative model. So let me first recap what is a discriminative model. And it's basically we have some features and we have some labels. We're going to find some function that links that can transform these features into the labels. So if the labels are kind of discrete, then we are focusing on those problems. They are machine learning. And if they are continuous, like stock price and so on, it's regression. And it's mostly dealt with in statistics. So we're going to focus on these classification problems, basically. And we usually represent these things by a bunch of weights and bias terms. And that's how we're going to figure out like a complicated function that represents these relationships. And I already talked about a lot of applications, so I'm not going to repeat all of them, but all the classification tasks, and we are actually doing these things in the programming homework, and one is classifying handwritten stuff, and the other one is given the patient information, how to figure out if the patient has breast cancer or not. And of course, all the recommendation systems, you can see those as based on the features of a person. Do you recommend this or do you not recommend this, and so on. And you have a lot of data on the rating from each person with different features, for example. And there are, again, lots and lots of applications. I'm not going to go through each one of them, but you can go through it and figure out like how they are related to the classification tasks. So what we had is basically, as I said, given our features, how are we going to predict our labels? And we can view this in terms of probabilities. So we have these activation functions. Remember, they are between 0 and 1. So we can view these as the probability that the class is 1 based on the features. And of course, 1 minus that will be the probability that it's class 0. That would be why when we are actually classifying stuff, we have this AI larger than or equal to 0.5. We classify it as 1, and otherwise we classify it as 0. So you can use this probabilistic representation too. What we're going to do here in the generative models is we're going to do the opposite. We're not going to base on x predict y. We're going to base on y and predict x. So let me explain this. So suppose we have a bunch of, say, cats again and dogs. I can think of more interesting examples. What we used to do is basically figure out a way to separate these two classes basically by some kind of function. And here what we're going to do is say, suppose we already know it's a cat. How are we going to generate these points? Like they all fall in some circle like this, and say they are most likely to be around here and maybe less likely to be around in that region. So we're going to figure out some kind of distribution of these images. And similarly, given the other class, we're going to figure out all of them are here, most of them may be at the center or something like that. So these things are this probability, basically given a label how to generate these features. And if you know Bayes' rule, then that, and of course I will explain this later when we actually talk about what all of these things are, we can go back and use this probability, use this generative probability to go back to calculate the original probability, and we are going to still use this thing to classify stuff. So we are always going to base on the feature, we calculate the probability of the labels, but where do we start is the problem. either we directly estimate a model that's this y given x, or we can estimate a model of x given y and somehow invert it using Bayes' rule, and then we will also get y given x. So that's the overview of what kind of stuff we're going to do. And of course, we're not going to get there like in one lecture. So this is basically next lecture. And this lecture, I will just have a brief review and like how it is related to natural language processing, usually written as NLP, natural language processing. And so the goal is basically how to generate new sentences based on the probability that we estimate from existing sentences. So that's the idea. Okay, let's get started. So first, if you are processing documents, of course we cannot use some kind of pixel information. Maybe we can like convert like each letter to something, but that may not make sense. So what we're going to do is we're going to convert each word to a number. The problem is what kind of number are we going to use? But before that, we need to somehow clean up this document because there are like spaces and punctuations that are not words, and there are things like these things that we don't really care, right? So how many thus are there in a document doesn't matter. Like it has nothing to do with the content of the document. And of course, capitalization, sometimes it does matter. Sometimes like us and US is different. But well, we assume that they are like similar. And well, and the other big problem that's actually hard to do is stemming. So if you have like looks, looked, and looking, you want to convert all of them to look. You will not do the last one for P3. So for P3, you'll only do the first three because the last one is kind of hard. You need some kind of dictionary to deal with these. Okay, so next we are going to introduce some terms. So first, a token is basically one occurrence of a word. So, but it can occur many times. So a token is just one of them, and the type is, well, it's just a unique token. So if a word occurs twice, there are two tokens, but there's only one type. And the list of types is called vocabulary, not surprisingly. And the problem with this is that the vocabulary is so large. So for P1, I am asking you to read a movie script. The vocabulary is huge, so instead of using like words as tokens, we're going to use characters as tokens. So this for P1. Oh, actually, sorry, not P1, P3. We're long past P1 now. Hopefully you finished it already. But well, anyways, P3, and we're going to use A as say a word. It's actually a character, but we are just going to assume that, and it will be a lot simpler. So I'll talk more about this in the next lecture. So one thing that's kind of interesting is the Zipf's law is the word count and the word rank. The rank means how frequent, like the ranking of the most frequent words in English or something like that. They are usually inversely related, and this relationship is called Zipf's law. It's not related to anything, but it's just a fun fact. So I just want to show it to you here, and maybe this one. So here, the image is too large, but it's okay. So here, the first one, the word rank is say number 1, is and the next one is I, and the next one is 2, and so on. So if you actually count it in some documents, and here is Romeo and Juliet, and if you actually count those, it shows this shape. And remember what this shape is just y is some constant over x. I mean, if this is x and this is y. So that just happens. It's no, like, it's not some mathematical result. It's just in most of the document, this kind of things happen, and we're going to call it Zipf's law. Well, just fun facts. And actually, now we're going to construct the features. So this is relevant information. So we have documents now. So a document can be like one sentence, or it can be actually be a document. A whole script could be a document. And a document is basically like, we used to call it one instance or an image in computer vision. That's why we're going to use I. And then there's a word J, it's like the feature J, but well, it's not actually feature J, but we will use the count of each word as the feature. So that's a better way to understand it. So given a document, we can basically count in the document how many times this particular word J occurs in the document, and then we divide it by the total number of words, and we call this the feature. Okay, so without a simple example, it's kind of hard to explain what this is. So let's assume we are reading, say, the script of, say, the movie Guardians of the Galaxy, and we only focus on what Vin Diesel said. And for the people who know this, it's basically just I am Groot, I am Groot, and maybe lots and lots of them, but I would just assume two of them. And then at the end, he said, "We are Groot." For the people who are completely lost, what's going on? What's Groot? I actually want to show you this Groot picture so that you can keep this in mind. This is a tree named Groot, or maybe a Groot named tree, but we're not going to talk about this. And so that would be our document number 1. And say document number 2 could be Guardians of the Galaxy Volume 2, or maybe I have another document, the Avengers Endgame or Infinity War. So I'm actually doing it in the wrong order. I apologize for the fans. So maybe let's not talk about all of them. I'll just say that I am Groot appeared once and so on. And maybe the same here and here. So what we're going to do is we are going to do X1. X1 is our feature for our first document, which is the script of Guardians of the Galaxy. And we're going to list out all the possible vocabulary, which is I am Groot, and we are, like that. So our first feature would be, I'm just counting how many times I happened. So I occurred twice, and there are in total how many words? 9 words. So that's the first value. And I am twice over 9, and Groot 1 over 3, because 3 times, and there are 9 words in total. And we, again, actually not twice, once. So that's our feature 1. So corresponding to the first document. And then our feature 2 is going to be the same. I am Groot, there are only 3. So I is 1/3 of the time, 1/3 of the time, 1/3 of the time, and 0, 0. And say X3 and X4, they are the same as X2. So they are all like 1/3, 1/3, 1/3, 0, 0. So this is basically called bag of words. Well, so I guess it's a very simple idea. And with this example, I think you know how to convert like these things into features. And of course, just like Zipf and Hog, there are like more complicated features that came from nowhere. And I'm going to introduce one of them, and we will never use this, but I still want to talk about it. So it's called Tf-idf features. So it's a long name. It's term frequency, inverse document frequency, Tf-idf features. And these features are basically replacing the count by kind of discount over the maximum, so it's kind of a fraction, and another count like this, counting how many documents contains this word, and then we have a log. So again, the choices of these things, why actually we are using these, is again given by some experiment with some particular documents. And in general, why are we going to multiply this has something to do with like information gain. Because if you look at it, this looks like a probability, and this looks like log of another probability. So it has some kind of relationship with information theory, but it's not clear how these probabilities come up like this. So there are explanations. If you read the Wikipedia page of Tf-idf, you can see some kind of information theory like related explanations. So I will not explain these here. And yes, so I explained what these notations mean, but you'll never be using this. Okay, so before I stop, I will talk about something else, is how to measure if two documents are similar. We didn't have this for images, but here we have this definition of similarity, usually called the cosine similarity, defined like this. It's basically you have two feature vectors. You can use the bag of words feature, or you can use the TF, whatever that one feature, and then you can just take the dot product and normalize it, and it represents basically the cosine of the angle in between the two vectors. And we use this to represent how similar two documents are.